Okay, in this video, guys, we're going to talk about Trig Sub. So it's a really interesting technique for integration, one that's really not that complex either. And so we'll get started by I'll just define a few ideas that we'll work with, and then once we get into some problems, you'll see how this all comes together. So if we ever run into the form a squared minus x squared, we're going to use a trig sub for x equals a sine theta. Okay, so a is some constant. If we ever run into an a squared plus x squared form, we're going to let x equal a tangent of theta. And then finally, an x squared minus a squared, we're going to use x equals a secant of theta. Now again, it might not make a lot of sense just seeing it on your screen right now, but once we get into a problem, by substituting this value for the x, what's going to happen is a trig identity is going to appear, in which case will allow the integral to hopefully simplify down a bit to where we can make better progress. All right, so as we take a look at our first example here, don't get blinded by the fact that we're in a trig subsection. Obviously, for any integral, run through your basic, simpler techniques first, but if it comes down to it, now we have this new technique. And so for us, what it looks like is this 5 plus x squared is going to be that a squared plus x squared that I had on the last screen. And so if that's the case, our a value would be the square root of 5, and so we would say x equals root 5 tangent of theta. Okay? Now, we're about ready to change variables. We're about to change from x's into thetas. So we need a substitution then for the dx as well. So that's going to be your root 5 secant squared theta d theta. So now I'll go ahead, every place I see an x, I'm going to plug this in. So I'll have an x squared there and an x squared there. And then my dx is going to be this thing right here. Okay? So we will have in the numerator 5 tangent squared theta. And in the denominator now, we're going to have 5 plus 5 tangent squared theta. And then the dx is being replaced with root 5 secant squared theta d theta. Okay, so now time to clean it up a little bit. First thing I'm going to do is take this 5 and pull it outside of the integral. So the 5 comes out. In the numerator, I'm going to have the tangent squared still. And in the denominator, I'm going to factor out a root 5 from this whole thing here. So the root 5 is going to come out, and then that's going to leave us with the square root of 1 plus tangent squared theta. We still have the root 5 secant squared theta off to the side. And right off the bat, the root 5s can go away. Okay? Now, the interesting part is right here, and this is how all these trig subs are meant to be. If you focus on just the inside here, just this 1 plus tangent squared, well, that's going to be secant squared. And so we have the square root of secant squared theta, which in theory does go to the absolute value of secant of theta. Now, for all of these problems, we're going to ignore the absolute value. Okay, so this whole piece right here is going to turn into just secant of theta. The reason why we're going to ignore the absolute values is, of course, because of the domain restrictions. So I would encourage you to take a look at the absolute value description in the book on page 467. They talk about the restrictions, and they talk about under these conditions, we can ignore the absolute value. Okay? So let me continue down just a little bit into this next step. I still have a tangent squared on top. And in the denominator now, I have that secant to the first, and then our secant squared theta d theta off to the side. Okay? So now, having done that, this secant and one of those can divide off. And so what I'll be looking at now is just a tangent squared times secant d theta. All right, so once I get to this point, I'm going to stop now and just remind everybody kind of where this whole thing started. We saw the 5 plus x squared, and so we made our substitution based upon what I talked about on the last screen. Not really having any knowledge to this point of why we did that. Now by plugging it in and simplifying, one of our Pythagorean identities will appear. because the Pythagorean identity appears and it's under that radical, that's where we get just the secant of theta. Once I substitute it in, now we're down to what is hopefully a much simpler integral. Now it's going to be a trig integral, of course, so we're going to have to make sure we use our identities correctly here as well. So to continue this, the tangent squared is going to be a secant squared theta minus 1, and we still have a secant theta, d theta. And then if I distribute, I get a secant cubed theta minus secant theta. Now, both of these integrals we've done in the past. This one just so happened to be circulating integration by parts, and this one is where we multiplied top and bottom by something. So you can certainly work those out again if you need to, but because we've done them before, I'm just going to go ahead and jump to the next step. I'm going to have a 5 out in front, and then for the secant cubed, that was that 1/2 secant theta tangent theta plus 1/2 natural log absolute value secant theta plus tangent theta. And then we'll have our minus, and then the integral for secant would be the natural log of the absolute value of secant theta plus tangent theta. And then I'm also going to tack on the plus c there at the end. And we can actually clean this up a little bit. You can see I have 1/2 here. I have a minus 1 right here. So when I combine that, I'm going to get a minus 1/2. I think now's probably a good time as well to distribute the 5 in there. So we'll have a 5 secant theta tangent theta, 5/2 secant theta tangent theta, and then minus a 5/2 natural log of the absolute value secant theta plus tangent theta plus c. Now, this isn't quite our final answer. Remember, we started in x's, so we have to go back into x's. So when you come over here and you look at this blue stuff, this stuff right here is going to allow us to construct a triangle. So our triangle might look something like this, and it'll be a right triangle. And we know from this guy right here, from our original substitution, this is always where you want to get your information from. Once you establish this as your initial substitution, you're going to use this guy for the rest of the problem, okay? That tells us that tangent is equal to x over 5, which means that this would be our x, this would be our root 5, and then using the Pythagorean theorem, you could find out the hypotenuse is going to be the 5 plus x squared. Okay, so now we're ready to come over here and fill in the missing parts. So our 5/2 is still going to be there. And then secant. Well, secant is the reciprocal of cosine. Cosine would be the root 5 over the hypotenuse. So for secant, we're going to do the hypotenuse over the root 5. So that's going to be the square root of 5 plus x squared over root 5. And then for tangent, we define tangent from the start. That's going to be x over root 5. And then minus 5/2 natural log absolute value. That secant we talked about before was 5 plus x squared over 5, all square rooted. And then plus the x over root 5 plus c. And from here, you could certainly clean that up, and I would encourage you to. There's a few things that can go away pretty quickly. For example, you can see here that the root 5s and the 5 go away there, in which case you would just have the 1/2 x root 5 plus x squared. And then similar on the other one, I'm going to call this minus 5/2 natural log absolute value of root 5 plus x squared plus x all over root 5 plus c. And full disclosure, the book, depending on how picky my math lab can be, the book might give you this as a final answer. And you might be thinking, okay, well, where in the world did the root 5 go? Well, we've seen this in the past, right? Using our properties of logs, it could be log of the numerator minus log of the denominator, and that log of root 5 is a constant, so it could be absorbed here. So when it comes to the final answer, all three of these would be acceptable final answers. So just be clear on what you're presenting. Most of the time they can clean up a little bit. This last step down here is just something I want you to be on the lookout for.